Hello there. So we're going to move on to the next video here. This one's all about the big three equations. This is video 3 of 4. So today's purposes, this is going to be all about the big three equations. We're going to learn what they are, and we are going to problem solve using these big three equations. Let's jump into this. So the big three equations, they're going to involve a set of 5 variables, just so that you know. This is the first one, v or vf. You'll see them written both ways depending on the equation. This is final velocity. You'll see v naught or vi. This is the initial velocity. You'll have a, we've seen this already, acceleration. D with the arrow, you know this is displacement, and then time. So these are the 5 variables you'll see in your big three equations. Note with this, the first 4 are vectors. So when we're writing those ones down, we need to take into account the direction. So make sure you read the question carefully. So here we go. These are the big three equations. V equals v naught plus at, d equals v naught t plus a half at squared, and v equals v naught squared plus 2ad. So notice with these equations, each one has 4 of the 5 variables. So the first equation there, it's missing displacement. The second one's missing v final, and the third one's missing time. So if you're ever confused which of these equations to use, just look at which variable are you missing and do you just not care about. And a very, very important note, make sure to star this, highlight this in your notes. If you have acceleration in the question, you must use these big three equations. This is what loses a lot of marks for students. Whenever there's acceleration in the question, you have to use the big three equations. Many tried to do the v equals d over t, which was for velocity. That only works constant velocity. So if you have acceleration, you must use one of these equations. Let's try a few examples. So we've got a pump cow. It's accelerating from 1.5 meters per second at 0.3 meters per second squared. We want to know how far does it travel once it reaches 2.2 meters per second. The first thing that I would suggest doing is looking at these 5 variables and seeing what are we given in the question and what do we need. Let's read through the question and see what we're given and what we're looking for. So we've got a pump cow accelerates from 1.5 meters per second. So that's our v initial is 1.5, 0.3 meters per second squared, that's our acceleration. And it says how far did it travel when it reached 2.2. So that means our final velocity is 2.2. And how far, this is displacement. That's what we're looking for. So notice in this one, we weren't given time. We don't care about time. It's not asking for it. So you look for which equations does not involve time. That's this one. From here, we can just plug in some numbers. Do a little bit of algebra. I show the middle step here just so you can see what I'm expecting once you write this on the test. This is what I'm looking for. Initial equation, have to write the initial equation. Plug in the numbers, show me a little in-between step to see your work, and then the final answer. This is good. And notice I did 3 digits here. Again, I don't care, 2, 3, 4 digits, that's fine for your answer. Just don't write it as a fraction. I don't want fractions, must have it as a decimal. Another question, we got a box of crayons, accelerates from rest to 3.5 meters per second in 10 seconds. We want to know acceleration. Let's look and see what we're given. So it accelerates from rest. So that means it starts at 0 meters per second. And then it goes to 3.5. So that's our final velocity in 10 seconds. That's the time. We want to know acceleration. In this case, we're not caring about displacement. So we want to use the equation that does not involve displacement, which is this one. Notice, or you might have seen, maybe not, notice that I've dropped actually putting all the little vector arrows above each of these, the velocities and the acceleration displacement. I dropped putting the arrows because I told you this is just going to be tedious and it's going to take too much time. So at this point, if you write it out like this, that's fine. Don't worry about all the arrows. By now, hopefully you know what are your vectors and what are your scalars, since time's the only scalar here. So we're not writing the arrows, but make sure you know when you have to put direction in the answer. So plug in numbers, we get an acceleration of this. And again, normally we would write a direction for acceleration, but we're not given any directions in the question, so I can't put direction in the answer. Next one, we've got a stationary water bottle. It's given an acceleration over a distance. We want to know how long was it accelerating. So in this question, we are told it's a stationary water bottle. So if it's stationary or at rest, same thing. Initial velocity is 0. Acceleration is given. Distance is given, or displacement since it's in a straight line. How long was it accelerating? That's time. So again, which equation involves all 4 of those, but not final velocity. That's the middle equation up top. Let's plug in some numbers, do a little bit of algebra. If the algebra steps are confusing, come talk to me in class. I can hopefully explain some of those for you, but the algebra part you should be able to do by now, hopefully. So there's your time. That's how long it was accelerating. So there's your big three equations. Again, remember, those are the ones you need to use if you have acceleration. Anytime something is accelerating, you must use those big three equations. Otherwise, you will get that question wrong. You cannot do v equals d over t. Has to be one of these big three equations. We got one more lesson left, and it continues off of this one. So study hard for this one, because the next lesson is basically just a continuation of this. Today's clip is from the first Guardians of the Galaxy movie. I'm also a huge Marvel fan. That's another thing that you just should know about me. In this one, the Guardians are trying to escape from prison. So with this, try and guess, is this plausible physics or is this not plausible? I will press play, give it a go, and see what you think. Alright, so there you go. Short clip this time. Give it a thought. If you think it's wrong, what do you think is wrong? Alright, so this one has something that's actually a little bit more subtle than maybe you'll think. In this one, Rocket is turning off all the artificial gravity except what is inside of their chamber. And the part that is not correct with this is when the gravity's turned off, look at all these people. They start rising and floating up. Actually, what would happen is, if you turn off gravity, things don't just all of a sudden start floating out in space unless they jump. So like, for example, if one of those people was to jump and push off the ground, then they would start floating upwards. But if they're just standing there and they haven't pushed off the ground, turning off the gravity wouldn't actually cause everyone to float up. They would just stay on the ground until they ended up giving a little push and they'd start moving. So that's the subtlety with this is, yes, people do float when there's no gravity, but you still have momentum. You'd have to push off in order to move around. So that's the subtle thing with this one.